All right, here we go. So I'm going to go through these different questions in these notes about functions. All right, so it's a total of 5 pages. The first 3, and then we're going to skip a couple you guys are going to do in class, or that you've already done in class if you're watching this after. And then the homework at the end, which, again, I'm not going to do on a video, but I'll post the key so you can check your work after you submit it. So let's get started by looking at a couple of definitions that I'm hoping you guys remember from your days in algebra. So when it's talking about a set of pairs of input and output values, this is what we call a relation. And if we have a relation where each element of the domain is paired with exactly one element in the range, or another way you probably looked at it in algebra was as long as your x values do not repeat, then you can go from a relation to say it is a function. So that's a very specific relation. Also, if you hear screaming children in the background, don't worry, those are my kids, and they're enjoying a calm bedtime right now. All right. So, a couple of questions here. We're going to draw a graph first of a relation that is a function, and I'm going to draw the quadratic function. That's not the quadratic function. Good try. There we go. The parent quadratic function looks like this, our parabola. All right, you could have drawn any other function that you know. Many students will draw a linear function, right? A line. Excuse me. Now, for a relation that's not a function, what you really need to be thinking when you're looking at this not a function is I want you to be thinking fails the vertical line test. So this would be something you guys would have learned back in Algebra 1, that if you take your pen or pencil and move it across the graph, moving left to right, as long as there is never a vertical line that hits more than one point, then it is a function. Whether it's continuous or not, that doesn't matter. It would still be a function. So my first thought was to draw a circle with a radius of 3. As if I draw a circle with a radius of 3, you should notice that I'm going to fail the vertical line test, and I'll draw a line for you that fails. Like, for example, at x equals 1, right? This line here at x equals 1 passes through 2 points, a point there and a point here. So because of that, this is what we call a relation. Again, many different relations you could have drawn. All right, so as I mentioned already with the vertical line test, as long as your vertical line only touches in one spot or none, right? Again, there will be times where you have non-continuous functions, then it is a function. If it does fail the vertical line test, then we call it a relation. Okay, create a set of ordered pairs that represents a function. So if I'm just writing down ordered pairs and do 1, 2, 3, 4, 5, 6, 7, 8. All right, that definitely represents a function. Nothing ever repeats. If you want to get a little bit crazy, you can start repeating. Just make sure you avoid repeating your x values. If you repeat your x values with a different y value, that would, you'll notice, would violate the vertical line test and would be a relation. All right, so I'm going to do that right here. So if I do 1, 2, but then I do 1, 3, and then I'll do some other points, you'll notice that this has the same input of 1, but it has different y values, different outputs. So that would be failing the vertical line test. So this is a relation. Okay, same idea. I'm actually just going to use those values that I just did before. So 1, 3, 5, and 7 for my input. And then I believe this was 2, 4, 6, and 8. You could get more creative with your values if you wanted to do different ones. Again, feel free to repeat as long as you're repeating in the y values. So for my not representing, I'll do the same thing I just did. So this was 1, 4, and 6. Notice that I'm not writing 1 twice. I'm just writing it 1 time. But then 2, 3, 5, and 7 are my output values. But here's kind of the mapping that would be an issue, is you'll notice 1 is going to go to 2, and 1 is also going to go to 3 like we did in those ordered pairs, and that would be a red flag. So this is going to be a relation. Okay, Now, let's do a couple of questions together where we're looking at deciding whether each relation defines a function and state why or why not. The key thing here is knowing that phrase, if you have repeated inputs, that's going to violate the vertical line test, so it's not going to be a function. You can also refer back to the very first definitions and say as long as each domain is paired with exactly one element in the range, then you know it's a function. So looking here, we'll look at these x values, oops, moved on me, and these y values. And I notice that my x values are all going to one particular y value. Yes, I do have repeats. You can see we have 9 and 8 occurs twice with the different inputs 4 and 8, and then respectively 12 and 15. That's okay though, because as long as my x values don't repeat, we're okay. This is a function. Same thing in the second example. I get another repeat here with these 5s, but you'll notice all of my x values are unique, so this is a function. Now this one we do have a red flag. When I look at this, I see 2 instances, where the 9s are repeating as well as the 12s are repeating. So that's multiple areas, multiple times, multiple instances where this set of ordered pairs would fail the vertical line test. If you wanted to do a quick little graph, I can show you. So 9, 3, 9, 5, or if I did 12, 3, and 12, 7, you'll notice both of those vertical lines would pass through 2 points, so that fails the vertical line test. So this is actually a relation. This one here has 5 distinct points. They're not connected, so this is not a continuous function. But if you did the vertical line test, you would never have more than 1 point on any vertical line. So it is a function, even if it is not continuous. And then with this next one, it is continuous. And if I did my vertical line test, I know you can't see me, but I'm taking my pen and going across on the vertical line. I never hit more than 1 point, so this is a function. Okay, now take that a step farther. I've already mentioned the words, which I'm hoping you guys remember again. It should be a review. If we're talking about all of the set of the inputs or x-coordinates in the ordered pairs, this is called the domain. And a lot of students think, like when you're talking about functions, you're talking about domains. You can still have domains even if it's a relation. You're going to see here in a moment. Some of these we already did. All of them we already did. And we had one relation. And so we will still have the domain even if it is a relation. And same thing with the range. You can have it for a function or a relation. It's a set of all outputs or y values. So for the domain here, I'm just going to list these, and we call this roster notation, where you have braces, and you put -3, 4, 8, 12, and 15, and then you close it with another brace. Same thing for the range. What you guys would have learned in Algebra 1 is that you put it in numerical order, and if they do occur twice, in this instance 9 and 8 both occur twice, you do not need to write them twice, right? It's just the set of all the values, not like how many times it happens. So you'll notice that we didn't have to write them twice. And even in the mapping, right, they didn't write multiple 8s and multiple 9s. Okay, for the next one, the domain here, we have -6, -3, 0, 2, and 4. And then for the range, we have 3, 5, 8, and 9. Notice again, I'm not writing 5 twice. And this last one here with the table, right? This was the one that we said was a relation. So I'm going to write 9, 12, and 18. My braces are getting worse. Apologize. And then for the range, we have 3, 5, and 7. All right. Last one's for the graphs. Again, both of these were functions. The domain here is I'm going to list it from least to greatest, which is -6, -3, 0, 3, and 4. If you're wondering how I got those points or values, I'm taking a look at each of these points. Right, there are 5 of them, and the x values of all those points gave me the domain. So respectively, if I look at the y values for each of those, all right, starting thinking least to greatest, so my lowest y values are going to be actually both of these points have the same y value of -2. Then this point has a y value of 0. And both of these up here have the same y value of 5. So only 3 values listed for the range. All right. Now this last one is important because we haven't talked about it yet with domain or range. It doesn't have arrows at the end, so I'm not going to think that it goes on in either direction forever. But it does, even though there's no point, as long as it's not an open value or an open circle, it does actually touch. I should change that. It does actually touch these points here. So when I do my domain and range, I'm going to use something called interval notation. I don't know if you guys remember this from your days in algebra. Interval notation. It's probably the most, I say probably, I'll take that back. It is definitely the most important notation in terms of my experience teaching the upper level classes of pre-calculus and calculus. You'll be using interval notation the most, not just in this class, but in those classes. And so when I look at this, if you include a value, if you guys remember, you use what we call a bracket. So this would be included. And if it touches but doesn't include it, we'll see that with an open circle. We use a parentheses. All right, so this would be not included, or you could think open. All right, or in this one, you could think closed and open. Again, we'll get to that more. Okay, so I'm going to start at -9. That's my lowest x value. Moving left to right, I go all the way to +6. You'll notice we are including all of those values in between, so I'm going to use brackets to show that it's going to go from -9 all the way to 6, every value in between, right? Don't just think, oh, it's just the counting numbers or the integers. It's every single number, like 1.462, right, is also included. And then I put the brackets because it does touch and include -9 and 6. If you wanted to, I guess I could show a quick little example. If for some reason these were open circles, then you would just have the same thing, but it would be parentheses. So that's the only difference. Okay, for the range, again, I'm going to go back to they are filled in. The lowest y value is down here at -3, and the highest y value is actually all the way at this last point on the right, which is a +5. And we do include all the values in between, so that's why we use interval notation, and we touch -3 and 5, so I use brackets again. All right, so for the domain, you'll notice that I was talking about going from left to right. All right, that's least to greatest. And then I'm always going to teach you for range to go from bottom to top. All right, always least to greatest. Get in the habit of doing that. Definitely going to need to do that in your upper level classes. Okay, so this is something you guys are going to practice on your own. There's an application I'm going to have you guys do in some groups. So these last 2 pages are what we're going to finish with here. Excuse my dog barking at somebody. All right, so let's talk a little bit about function notation. You guys were first introduced to this idea of y equals some value for those equations. And then in Algebra 1, you were introduced to this it's just called function notation. It's fancy. It's just a more proper way of writing the same thing. So I used to think of when I'm teaching you guys, I'm wearing my shirt and tie, but when I'm at my house on the weekends, I'm not wearing a shirt and tie. It's still me, just wearing different clothes. So just one is a little bit fancier, but still the same. It's just the way that we name it is a little different. All right, so in this case, you'll notice f of x, I already said it, is read as f of x. We don't say f times x. All right, and you can be g of x, h of x. We have all different letters we can use. So when you're doing the not function notation, I'm going to just plug in that value of 3 and finish the evaluation to get 6 minus 1, which is 5. Hence the ordered pair 1, 5. Should say, sorry, 3, 5. Apologize for that. All right. Now this next one, right, same thing. I'll put the 3 there. I'm going to plug in 3. So it's 2 times 3 minus, oops, that's not how you write it, minus 1. So this is the fancier way of writing f of 3 equals 6 minus 1 equals 5. So you'll notice it's very similar. It's just different how we write kind of the notation. So one is f of 3 equals 5. That's function notation. And the other is just an ordered pair 3, 5. All right, so let's look at doing some of these together with some evaluating with function notation. So the first one is very similar to what we just had. It's f of 2. So I'm going to replace the x with that value of 2, right? This is replacing x. And doing my algebra, I get 6 minus 2, which is 4. So f of 2 equals 4. So if you think of this like probably when you were in middle school, it taught you functions for the first time. They talked about, maybe not, this is what we were taught when I was in school, was think of it as a vending machine. If I were to type in the button 2 into this vending machine, it would spit out the number 4. Okay? For part B, this one is definitely more challenging. We're going to plug in an expression into that x. So it's going to be a plus 5 into this g of x here. So I'm going to square it, because it should be that value squared, plus 3. Excuse me. So from here, I'm going to expand that, and I am going to teach you guys how to remember how to expand this if you don't already. If you needed to, and you needed to write a plus 5 times a plus 5, that is what squaring something means, to multiply by itself. Feel free to write that and multiply it all out. You'll get the same thing. But I'm going to start teaching you that if you have something like this, a plus b squared, that's the same as a squared plus 2ab plus b squared. So I'm going to think of this as the first term squared, the last term squared, and the middle term is the first term times the second term times 2. So a times 5 is 5a. 5a times 2 is 10a. So that's how I'm going to encourage you guys to expand these binomials. So it's a squared plus 10a plus 28. That is g of a plus 5. Again, you'll get more practice with that, and guarantee that's going to be on stuff that I assess you on because it's so important. Okay, this one's a little different, right? Remember, this is just a fancy way, f of x, of saying the letter y. So I'm going to rewrite 3x minus 2, but this time it doesn't tell me to plug in a value for x. It tells me, okay, what is the x value I would need to make this function become negative 20? So I'm going to set the function equal to negative 20, and then use my understanding of solving linear equations to find what that x is. So if I add 2 to both sides, I get negative 18, so x is equal to negative 6. And if you wanted to check your work and plug in negative 6 back where it says x, you would see you get negative 20. Same thing with part D, plugging in 2/3 where it says x, I get 2/3 squared plus 3. Remember, squaring a fraction, just square both the top and the bottom. So the numerator squared is 4, denominator squared is 9. All right, I'm going to go ahead and get a common denominator for that 3. If this is over 1, getting common denominator would be a denominator of 9. To get from 1 to 9, I multiply by 9. So 3 times 9 is 27. That shouldn't surprise you, right? Because ultimately, if you were to divide 27 divided by 9, you would return back to 3. Now I can add the numerators, keep the denominator the same to get 27 plus 4, which is 31/9. If you would like to write that as a mixed number, feel free. Improper fractions, totally fine. Okay, similar to what we did with part C in this part E, I'm going to set my g of x function, which is x squared plus 3. So x squared plus 3. Set that equal to 19. So what x values would make this true? Move the 3 over with subtraction to get 16. Hopefully you guys remember to get rid of that square. The inverse operation is the square root of both sides, which gives me x equals, people are going to say 4. And this is one of those things that I'm going to try to make sure you understand, that if you take the square root of both sides, which we just did in our steps in this problem, if you do that in your math, you need to make sure that you put plus or minus. Because if I were to take positive 4 and plug it back in here, or negative 4 and plug it back in, squaring each of those numbers would give me 16. And 16 plus 3 would give me that 19. So both are actually correct. And last but not least, let's plug in 1/4 into f of x. So it's going to be 3 times 1/4. I believe it's minus 2. It is. So that's going to be 3/4 minus 2. Same thing I just did before. Get a common denominator. Here would be 4. To get from 1 to 4, I multiply by 4. So 2 times 4 gives me 8. Always remember to take a moment, divide. Alright, I'm going to try using Loom to see if I can finish this video, even if it's a little bit laggy. I apologize, but Camtasia Tech, whatever it is giving me some fits with my audio, and I'd rather it be a little bit off, but I don't sound terrible. Alright, so I was here finishing f of 1/4. I wanted to get a common denominator to subtract these, a denominator of 4. So getting from 1 to 4 is multiplying top and bottom by 4 to get 8/4. Don't forget to reduce this, and you should go back to that too. So f of 1/4 is equal to negative 5/4. All right, this last page is looking at two graphs of function. We have a quadratic and then a piecewise function, and we're going to plug in some values, evaluate them, as well as find some x values that would make the function become certain values. So in this case, if I plug in 1 into my g of x function, I'm going to go on the x-axis where it is 1, find a point that is on that graph when x is 1, and that y value is negative 2. Same thing for h of 1, plugging in 1 for x. You'll notice that actually, if I go here, you might think there are actually 2 points, but there are not because of that open circle. It's not included at 1, 5. So I always think of, like, if I'm traveling on this blue line, left to right, when I get to that open circle, I jump down to this point and then continue on the red line. So 1, 1 would be that answer. Now for these where you're asked to set the function equal to a value, I always think of this as y equals 6. So if I were to plot the horizontal line, y equals 6, and then find the x values that are at those values or those points where the function intersects that line, that's going to be this x value and this x value, which is going to be a negative 3 and positive 3, or plus or minus 3. For the next one, if I plug in negative 5, it's actually off the grid, right? If I keep moving down with that blue line. So I think I made a mistake here, but I'll just go ahead and do it. If I look at starting at the y-intercept and moving 1 to the left and 1, 2, 3, 4, 5 down, 1 to the left, 1, 2, 3, 4, 5 down, you can see if I followed that slope, I would get negative 3, comma, negative 15, then negative 4, comma, negative 20, and then negative 5, comma, negative 25. I don't expect you to do this on any assessments I would give, so if I actually rewrote this as h of x equals negative 5, what x values would work there? So plotting a horizontal line at negative 5, you can see my 2 points are going to be here on the function, which those x values would be negative 1 and positive 4. Okay, so that makes a little bit more sense. All right, last but not least, if I plug in 0 for my g of x function, that's going to be the point here, 0, comma, negative 3, or the y-intercept. And then for this last one, let's go ahead and do y equals 5. But what's interesting about this one is that it actually doesn't hit anything because of that open circle. There's not a point that has a y value of 5. There's a point really close to it that gets to a y value of like 4.9 repeating, but I never actually get to 5 because it's not included. So there actually is no x value to make this. So I'm going to put does not exist. All right. So again, I apologize for the different parts here, but hopefully you've watched them. And don't forget to submit the homework onto Canvas.